Hello everyone. Myself Mr. S.M. Ganwat, working as Assistant Professor in Mechanical Department in Sharad Institute of Technology, College of Engineering, Yadra. Today we are going to discuss atomic structure and interatomic bonding. In part first, we are going to discuss why to study atomic structure and interatomic bonding. Then we are going to discuss the fundamental concepts. Then we are going to discuss electrons in atoms. Now we will start with our first point, why to study atomic structure and interatomic bonding. An important reason to have an understanding of interatomic bonding in solid is that in some instances the type of bond allows us to explain a material's properties. For example, consider carbon, which may exist as both graphite and diamond, whereas graphite is relatively soft and has a greasy feel to it. Diamond is relatively hardest known material. In addition, the electrical properties of diamond and graphite are similar. Diamond is poor conductor of electricity, but graphite is a reasonably good conductor. These disparities in properties are directly attributable to a type of interatomic bonding found in graphite that does not exist in diamond. Therefore, it is essential to study atomic structure and interatomic bonding. Also, we have discussed the four components that are processing, structure, properties, and performance. In this particular scheme, the reason for studying atomic structure and interatomic bonding are as follows. For example, for silicon, its electron configuration determines the type of primary bonding, which in turn affects its electron band structure. Also, we'll discuss another example of polymer fiber. For polymer fibers, electron configuration of the constituent element affects the type of primary bonding. Bonding type has an influence on the structure of polymer molecules. Therefore, number of reasons are there where it is essential to study atomic structure and interatomic bonding. Therefore, in this session, we are going to discuss why atomic structure is essential, what is interatomic bonding, and by studying all those things, it is possible to utilize this knowledge to perform the given application. Now we will move further with the next point, that is fundamental concepts. Some of the important properties of solid materials depend on geometrical atomic arrangement and also the interaction that exists among constituent atom or molecules. Now we will start with the fundamental concepts. Each atom consists of a very small nucleus. Again, this nucleus is composed of protons and neutrons, which is encircled by moving electrons. I will repeat this particular concept. Each atom consists of very small nucleus, which is composed of protons and neutrons, which is encircled by moving electrons. Both electrons and protons are electrically charged. The charge magnitude is being 1.602 into 10 raised to minus 19, which is negative in sign for electrons and positive for protons. Neutrons are electrically neutral. Masses for these subatomic particles are infinitesimally small. Protons and neutrons have approximately the mass of 1.67 into 10 raised to minus 27 kg, and which is same for both. which is significantly larger than that of an electron, having mass of 9.11 into 10 raised to minus 31 kg. Now we are going to discuss the next concepts, that are atomic number, atomic mass and isotope. We'll start with the atomic number. Each chemical element is characterized by the number of protons in the nucleus, or the atomic number. Means every chemical element has got number of protons in the nucleus, and that is termed as the atomic number. And the atomic number is indicated by the letter capital Z. Once again, I am going to repeat this atomic number as: each chemical element is characterized by the number of protons in the nucleus, and this is nothing but the atomic number, which is indicated by the letter capital Z. For an electrically neutral or complete atom, the atomic number also equals the number of electrons. This atomic number ranges in integral unit from 1 for hydrogen to 92 for uranium, the highest of the naturally occurring element. Now we are going to discuss what is atomic mass, which is indicated by letter A, capital A. The atomic mass, that is capital A, of a specific atom may be expressed as the sum of masses of protons and neutrons within the nucleus. I will repeat this atomic mass. The atomic mass of a specific atom may be expressed as the sum of the masses of protons and neutrons within the nucleus. Although the number of protons is the same for all atoms of a given element, the number of neutrons may be variable. Thus, atoms of some elements have two or more different atomic masses, which are called as isotopes. Means the atoms of same element have two or different atomic masses are termed as isotopes. Now we will move further with the next point, that is the atomic weight of an element corresponds to the weighted average of the atomic masses of the atoms naturally occurring isotopes. The atomic mass unit, we call it as AMU, may be used to compute the atomic weight. A scale has been established whereby 1 AMU is defined as 1/12 of the atomic mass of the most common isotope of carbon, that is carbon-12. Within this scheme, the masses of protons and neutrons are slightly greater than unity, and we can write it as A is approximately equal to Z plus N, where A is nothing but atomic mass, which is again approximately equal to Z plus N. Z is nothing but the atomic number, which is nothing but the number of protons in the nucleus, or we call it as atomic number, that is indicated by letter capital Z. And N is nothing but the number of neutrons. Therefore, we can say that the atomic mass capital A will be approximately equal to the atomic number plus number of neutrons, where atomic number is nothing but the number of protons. Means atomic mass A will be approximately equal to number of protons plus number of neutrons. The atomic weight of an element or the molecular weight of a compound may be specified on the basis of AMU per atom. AMU is nothing but atomic mass unit, or mass per mole of material. We will move further with the next point. In 1 mole of a substance, there are 6.022 into 10 raised to 23 atoms. This number is called as Avogadro's number, or I can repeat it. In 1 mole of a substance, there are 6.022 into 10 raised to 3 atoms or molecules. This particular number is also termed as Avogadro's number. These two atomic weight schemes are related through the following equation. The equation is 1 AMU, that is atomic mass unit per atom or molecule, will be equal to 1 gram per mole. For example, the atomic weight of iron is 55.85 AMU per atom or 55.85 gram per mole. Sometimes use of AMU per atom or molecule is convenient. On other occasion, gram or kilogram per mole is preferred. Now, once again, we will repeat the concept of mole. In 1 mole of substance, there are 6.022 into 10 raised to 23 atoms or molecules, which is termed as Avogadro's number. And the equation that we are going to utilize is 1 AMU per atom or molecule will be equal to 1 gram per mole. And we have seen the example of atomic weight of iron, that is, I can represent the atomic weight of iron in terms of AMU per atom or gram per mole, which is of 55.85, and sometimes use of AMU per atom or molecule is more convenient than use of gram per mole. Now we will move further with the next point, that is electrons in atoms, or we are going to discuss the atomic models. During the latter part of 19th century, it was realized that many phenomena involving electrons in solid could not be explained in terms of classical mechanics. What followed was the establishment of a set of principles and laws that govern systems of atomic and subatomic entities that came to be known as quantum mechanics. Therefore, quantum mechanics plays an important role, which is nothing but the establishment of a set of principles. An understanding of the behavior of electrons in atoms and crystalline solids necessarily involves the discussion of quantum mechanical concepts. One early outgrowth of quantum mechanics was the simplified Bohr atomic model, in which electrons are assumed to revolve around the atomic nucleus in discrete orbitals, and the position of any particular electron is more or less well defined in terms of its orbital. The schematic model of this Bohr atom is shown in figure. Once again, we are going to discuss Bohr atomic model, in which electrons are assumed to revolve around the atomic nucleus. It is our first point in discrete orbitals, and the position of any particular electron is more or less well defined in terms of its orbital. Now we are going to discuss the electron energy state for Bohr hydrogen atom and electron energy state for first three shells of wave mechanical hydrogen atom. Another important quantum mechanical principle stipulates that the energies of electrons are quantized. That is, electrons are permitted to have only specific values of energy. An electron may change energy, but in doing so, it must make a quantum jump either to an allowed higher energy with absorption of energy or to a lower energy with emission of energy. I will repeat this particular concept once again. Electrons are permitted to have only specific values of energy. An electron may change energy, but in doing so, it must make a quantum jump either to an allowed higher energy with absorption of energy or to a lower energy with emission of energy. Often, it is convenient to think of these allowed electron energies as being associated with energy levels or states. These states do not vary continuously with energy. That is, adjacent states are separated by finite energies. For example, allowed state for the Bohr hydrogen atom are presented in figure. These energies are taken to be negative, whereas the zero reference is the unbound or free electron. Of course, the single electron associated with the hydrogen atom will fill only one of these states. Thus, the Bohr model represents an early attempt to describe electron in atoms in terms of both position and energy. For position, it is electron orbitals, and for energy, it is quantized energy levels. Now, we are going to compare Bohr and wave mechanical atom models in terms of electron distribution. The Bohr model was eventually found to have some significant limitations because of its inability to explain several phenomena involving electrons. A resolution was reached with a wave mechanical model in which the electron is considered to exhibit both wave-like and particle-like characteristics. With this model, an electron is no longer treated as a particle moving in a discrete orbital. Rather, position is considered to be the probability of an electrons being at various locations around the nucleus. In other words, position is described by a probability distribution or electron cloud. This is the major difference in Bohr model and wave mechanical model. In Bohr model, it is found that it has got inability to explain several phenomena involving electrons. Then a wave mechanical model was developed in which the electron is considered to exhibit both wave-like and particle-like characteristics. With wave mechanical model, an electron is no longer treated as a particle moving in a discrete orbital. Rather, position is considered to be the probability of an electron being at various locations around the nucleus. In other words, the position is described by a probability distribution or electron cloud. The figure is going to show you the comparison between Bohr and wave mechanical model for hydrogen atoms. Now we are going to see the reference part. For this session, the reference is William D. Callister Jr., David G. Rethwich, Material Science and Engineering, an Introduction. For further reading, you can refer this particular reference book for Introduction to Material Science and Engineering. Thank you.